We usually think of a planetary surface as a place with a clear horizon and a sky that reflects the light of its star, but it turns out, on Venus, the atmosphere is so thick that the sky essentially disappears. The Soviet Venera landers showed us a world where the laws of optics are broken by a crushing orange fog. We generally describe the atmosphere of Venus as a gas, but once you descend below the cloud decks, that definition starts to fail. At the surface, the pressure reaches 93 bars. For context, that's about 90 times the pressure at sea level on Earth. But interestingly, this pressure, combined with temperatures of 460 degrees Celsius, pushes the carbon dioxide past its critical point. It becomes a supercritical fluid. This means it has the high density of a liquid, but fills space like a gas. If you were standing there, the air wouldn't feel like air. It would feel like being 900 meters deep in a terrestrial ocean. But just so we're clear, this isn't water. It's a caustic, high-energy fluid that fundamentally changes how physics works on the ground. For instance, the way heat moves through this fluid is incredibly efficient, which is why the temperature is so uniform across the entire planet. But more importantly, the density of this supercritical CO2 creates a massive index of refraction. And this leads to one of the stranger observations from the Venera missions. On Earth, the horizon appears to curve away from us. But on Venus, the dense atmosphere bends light so intensely that the horizon actually appears to curve upward. It's a phenomenon called superrefraction. If the light could travel far enough without being absorbed by the haze, you might technically be able to see the back of your own head. But interestingly, the light doesn't make it that far. The atmosphere is so thick and the scattering is so intense that your field of vision is restricted to a tight, distorted bowl. So, while we think of Venus as a sister to Earth, the reality on the ground is more like a deep-sea floor. But interestingly, the light that actually makes it to the surface isn't what we'd recognize as daylight. On Earth, we're used to Rayleigh scattering, the process that makes the sky blue by scattering shorter wavelengths. But on Venus, the Venera 11 and 12 missions use scanning spectrophotometers to look at the light profile during the descent, and they found something strange. As the lander dropped below 30 kilometers, the blue part of the spectrum simply vanished. And so, by the time you reach the ground, there is a total 450 nanometer cutoff. The atmosphere acts as a massive chemical filter. It's not just that it's cloudy, it's that the specific concentration of sulfur aerosols and the sheer density of the supercritical CO2 absorb all of the shorter blue wavelengths of light. This leaves only the longer red and orange wavelengths to reach the surface. So, when the Venera landers turned on their cameras, the landscape didn't look like a desert on a cloudy day. It looked like a world lit by a dim, orange heat lamp. But just so we're clear, even though the sun is blocked, the surface isn't dark. It's actually quite bright, about the same level of illumination as a heavily overcast day in the mid-latitudes on Earth. But the quality of that light is fundamentally different. The Soviet scientists had to account for this by using color calibration targets, basically small boards with known color swatches, that were visible in the corner of the lander's cameras. But interestingly, when they compared the raw images to those targets, the red tint was so heavy that the white sections of the target appeared orange, and this has led to a long-standing debate. If you could somehow clear the atmosphere, the rocks themselves would likely be gray or black basalt. But under that sky, everything is stained a deep, monochromatic rust. But interestingly, even though the light is distorted, the physical samples tell a much more grounded story. We usually imagine Venus as a completely alien landscape, but when Venera 13 and 14 deployed their drilling rigs, they found chemistry that looks remarkably like home. These landers were equipped with X-ray fluorescent spectrometers, tools designed to bombard the soil with radiation and measure the secondary X-rays emitted back. And so, for the first time, we got a definitive look at the mineralogy of the Venusian plains. The data showed that the landing sites were primarily composed of tholeiitic basalts. On Earth, these are the exact same types of rocks you find on the ocean floor or in the volcanic chains of Hawaii. But just so we're clear, there was a slight variation between the two sites. Venera 13 landed in an area with high potassium alkaline basalts, which are much rarer on Earth and usually associated with deep-seated rift zones. So, what this tells us is that the ocean floor of Venus is actually a massive basaltic crust that has been shaped by horizontal volcanic flows. But interestingly, the physical state of these rocks was unexpected. The cameras showed plates of rock that looked like broken pavement, separated by dark, fine-grained soil. Because the atmosphere is a supercritical fluid, it doesn't just sit on the rocks, it chemically attacks them. The Venera landers recorded a surface that was surprisingly crisp. There wasn't the kind of rounded, windswept erosion we see on Mars. Instead, the rocks had sharp edges, suggesting that the weathering on Venus is a slow chemical transformation rather than a mechanical one. And yet, the wind sensors on Venera 13 measured speeds of only about 0.5 meters per second. On Earth, that's a light breeze. But on Venus, because the air is so dense, that breeze carries the force of a heavy current. It's enough to drag pebbles across the basaltic floor, slowly grinding the pavement into the fine, dark dust that filled the cracks between the plates. But interestingly, the most controversial part of the Venera data didn't come from the sensors themselves, but from a re-examination of the raw telemetry decades later. In 2012, Dr. Leonid Xanfomaliti of the Russian Academy of Sciences published an analysis of the Venera 13 panoramic images. He used modern digital processing to look at low-resolution artifacts that had been ignored for 30 years. And what he found was a series of transient objects, most notably a disc-shaped feature, a black flap, and a shape he described as a scorpion. But interestingly, these shapes weren't there in every frame. They appeared to emerge from the soil, remain visible for a few minutes, and then vanish. So, the question is, how do we actually know what these were? Most of the scientific community pointed to a more grounded explanation. When the Venera landers touched down, they blew away the surface dust with their landing shock. But just so we're clear, the lander also ejected several components upon impact, including the lens caps and parts of the drilling mechanism. The consensus is that the moving objects were likely just pieces of the lander's own hardware that had been caught in the dense, heavy wind and dragged across the field of view. But Xanfomaliti argued that the shapes were too symmetrical and showed behavioral patterns that didn't match simple windblown debris. So, we have a mismatch. On one hand, you have the physical reality of a 460 degrees Celsius environment, where conventional life is impossible. On the other, you have visual data of objects that appear to move independently. But interestingly, even if these aren't living things, they tell us something about the surface. If they were indeed lens caps or debris, the way they moved through the supercritical fluid suggests that the atmosphere is far more dynamic than the slow wind speeds suggest. It's a world where even a tiny breeze has the kinetic energy to relocate heavy metal components across a basaltic plain. But interestingly, when you leave the flat basaltic plains of the Venera landing sites and look at the Highlands, the rules of the surface change again. While the landers only saw the lowlands, we have radar data from the Magellan mission that found something that doesn't make sense at first. On Earth, mountaintops are white because of water ice, but on Venus, where the temperature never drops below 400 degrees Celsius, ice is physically impossible. And so, we have a mismatch. If you look at the radar maps of mountains, like Maxwell Montes, the peaks are incredibly bright, meaning they are highly reflective to radar. This usually implies a metallic coating. But just so we're clear, this isn't a thin layer of dust. It's a literal frost of heavy metals. Because the atmosphere is a supercritical fluid, it's capable of dissolving metals like lead and bismuth from the rocks at lower, hotter elevations. So, as the air rises and cools, relatively speaking, these metals reach their condensation point. It turns out that it snows metal on Venus. The peaks are likely coated in galena, which is lead sulfide, and bismuthinite, or bismuth sulfide. This creates a world where the mountains aren't just high, they are electrically conductive. But interestingly, this process also suggests that the atmosphere and the surface are in a constant state of chemical exchange. The Venera missions gave us a glimpse of a world that is essentially a giant, planetary-scale chemical reactor. The main idea we've gathered from these Soviet probes and later radar mapping is that Venus isn't a dead rock. It's a place where the air behaves like a liquid, the sky filters out the color blue, and the mountains are capped with metallic snow. But interestingly, as we look toward future missions like Da Vinci and Veritas, we're starting to ask if this was always the case, or if we're looking at the final, suffocated stage of a planet that once looked exactly like Earth.